And again, most stimulating talk by Professor Ignacio Cirac from the Max Planck Institute for Quantum Optics. I know you want to hear him, so I will not list his many honors, etc., but let him speak about science. Professor Cirac.
Thank you very much. So it's a great pleasure to be here, and this is why, first of all, I would like to thank the organizers of this conference for this very kind invitation, and in particular to Professor Levine for this invitation as well. So my talk is going to be about quantum simulation, like the previous talk that you just had. However, I'm going to take a different route. I'm going to look at the problem of many body systems, like the Hubbard models that were mentioned in the previous talk, or some other models. And I want to ask the question, so are they really difficult? So can we solve them with classical computers, or do we need a quantum computer to solve them? And if we need a quantum computer, so what is the price we have to pay in terms of time? Will it be work right away much better than a classical computer, or will it still be kind of difficult to solve this kind of problems? So let me start just talking first about quantum computers. So you probably have heard that now for many years, many people are dreaming of having such a computer. That's a computer in which, instead of working with the classical laws, you will work based on quantum laws. So instead of bits, we have qubits. The information is not encoded in bits, it's coded in qubits. And instead of having logic gates, we have quantum logic gates, because they have to manipulate the quantum states of these qubits in such a way that we can solve problems in a more efficient way than with classical computers. In fact, we know by now many applications of such quantum computers. So if we had one of those computers, then indeed this would be very useful. At the moment, however, we don't have one of those computers. We have kind of prototypes of such computers. And so these are, on the one hand, what we call analog quantum computers. So they don't work based on quantum gates or in the same way as these quantum computers that I just mentioned. And this would be kind of the equivalent to analog computers that were developed like 100 years ago, and now we have them at the quantum level. So an example of that is the ones based on cold atoms that were mentioned in the previous talk. There are also what's called noise intermediate scale quantum computers. These are quantum computers that are digital, so they are based on qubits, they are based on gates, they are discretizing the time. However, they are noisy and they are not scalable. And so they cannot fulfill all the goals that the quantum computer would, and in particular, it cannot run the algorithms that were developed for quantum computers. However, it can, both of them, both analog and NISQ computers, the one that we have now, they have shown already that they can solve certain particular tasks more efficiently than classical computers. So one of the questions that is now very popular in the field of quantum computation is whether these analog and NISQ computers, the one that already exists, would be useful for some other tasks before we build these scalable digital quantum computers that will still take some time. And so I want to talk a little bit about that, and in the context of quantum many-body problems. So we know that in quantum physics, when we have many particles, then typically these problems are very difficult to solve with classical computers, at least if you want to solve them exactly. So these problems pop up in chemistry when you have many atoms and many electrons interacting with each other. They also appear in condensed matter physics, where you have that atoms are maybe fixed on some lattice, but the electrons can move, or maybe the electrons can interact through the spins. And they can also happen in some other fields, like high energy physics, where even the equations of the standard models contain like many body, all these quarks, gluons, and so on, will be apparent there. And all these problems have something in common, is that when we try to solve them, the first thing that we do with them is to put them in some kind of lattice, so we discretize the space in one way or another. And looking at the principles that we know from chemistry or for physics, then we write some Hamiltonian that tells us how the particles that are on this lattice interact with each other. So for example, if we are trying to model a material in which the magnetic interactions are important, then we probably will have the original lattice in which the material is formed, and we will just put one particle one spin in each of these lattice sites, and the Hamiltonian will tell us how these spins interact with each other magnetically or by exchange interaction or whatever other means. And if we want to study and make predictions of that systems, then we have to follow the rules of quantum mechanics. So this means that all the physical properties will be encoded in the state of the system, let's say in the wave function of this system. And even we have the simplest description that is possible for such a quantum system, in which these particles that we put at each of the nodes are spin 1/2 particles, what we call qubits, that can take two values, like spin up and spin down, plus superpositions. Then we realized that there are many classical configurations. So for example, we could have a configuration in which all the spins are down. This is what we will call the state 0, 0, 0, or all the spins are down and the last is up. This would be 0, 0, 0, 0, 1. And you can count and you see that there will be 2 to the power n different configurations. And so this means that the state that represents the physics that we want to describe will be a linear superpositions of these possible configurations. And therefore, all the physical properties will be encoded in the coefficients of the superpositions. So in other words, if we want to solve this state, we will have to find these coefficients. And since there are 2 to the power n configurations, even in the simplest case, where n is the number of lattice sites, then we will have to compute 2 to the power n coefficients. And this is a number that grows exponentially with the lattice size, with the volume, with the number of particles that we have. And that's typically very bad, because as soon as n is of the order of 30, 40 or something like that, we run out of resources. And what is important to notice is that we run out of many resources. So first of all, if we want to solve this problem, we will have to store these coefficients in the memory of our classical computer. And since there are 2 to the n coefficients, then we will need a memory that grows exponentially, again, with the size of our system, with n. At the same time, if we want to do any prediction, we will have to make some computation with these coefficients, or we will have to compute the coefficients themselves. And the computations, the number of computations would be at least the number of coefficients. And since there is an exponential number of coefficients, this means that the computational time will also grow exponentially with n. So we have a quite bizarre situation in which both the memory and the time grow exponentially with the number of qubits that we have, with the size of our system. So typically, in many problems in classical physics, we can have that the time grows exponentially, but the memory not. The memory can grows just linearly with the size of your system. And so, in fact, if you can trade time for memory or memory for time. So, for example, imagine that you have now a classical computer that has a limited memory, that it has, let's say, the memory is equal to the number of atoms that we have on the Earth, on the planet Earth. We cannot imagine that we will build a computer larger than that. Then, with this, then we could still solve even without growing the memory. So there are ways of trading time. And in this case, then it happens that the time that it requires to solve this kind of problem grows super exponentially, like 2 to the n to the power n with the system size. So we see that quantum many-body problems are extremely difficult because of this memory and time. The constraints is not only one of them. And that's where quantum computers can make a very big impact. And this is something that, as was mentioned in the previous talk, was already realized by many people in the past, in particular, Richard Feynman, in the context of lattice gauge theories. Then he realized of this problem, and he says that we can save at least the problem related to memory just by using quantum bits instead of bits. Or in other words, if we want to describe a problem that is quantum mechanical and in which we have quantum bits on a lattice, why don't we take another system which we can tame and that it's made out of qubits, and then prepare the state that we have, the quantum simulator, in the state that we want to investigate. And so in this case, if we want to make some predictions on some state, we will prepare our simulator in this particular linear combination, and therefore we will need only n qubits. And so you see that right away, just by using quantum machines instead of classical machines to solve quantum problems, then our memory grows only linearly with the size of the system, not exponentially. And the question is now, how does the time scale? And this is what I want to address in this talk. So how in these quantum simulators the time grows. It could be linear, maybe it's exponential, maybe it's something else. And I want to see for different problems how this time scales on quantum computers. So that's a bit of the outline of the talk. So I consider now lattice systems. So I assume that one has done the exercise already of translating the physical problem or the chemistry problem into some lattice. And in this lattice, we are giving some Hamiltonian. And this Hamiltonian is typically a sum of terms. So these are Hamiltonian that are acting on some regions of the lattice, or maybe you have Coulomb interactions. They will be long-range interactions, but only involving very few of these qubits, only few of these particles. And I want to revise quantum algorithms that solve these problems with quantum computers. And the type of problems that I want to study are, first of all, dynamics. So what happens if I start with some initial state of my system and I want to predict what will be the physical properties of my system in the future as it evolves according to this Hamiltonian? Or I want to also study algorithms that solve equilibrium properties. So what happens now if my system is in thermal equilibrium, it's at finite temperature or is at zero temperature? So how can I predict the properties of my system in those conditions? And then in the last part of my talk, I will briefly mention some applications of these analog quantum simulators in the fields of condensed matter physics, high energy, and chemistry. So again, I'm going to describe these algorithms. I'm going to say what it's known, and very superficially. And then I will concentrate on what is the computational time that they require. And I will also mention whether these algorithms work for analog or niche devices, or indeed one needs what requires a scalable quantum computer for them. Okay, so let me start talking about quantum algorithms in general, and let me go to the first one. The first one, again, is that somebody gave us this lattice and tells us what is the Hamiltonian. It also tells us what is the initial state. So this could be, for example, some product state. If these were spins, this could be, for example, all our spins up, or maybe half of the spins are up and half of the spins are down. That's a state that we require to be easy to prepare with a quantum computer. So that's something that, for example, if it's all spins down, this would be very easy because it would correspond to prepare our quantum computer or simulator, like with all the qubits in zero. And then we would like to evolve according to a Schrödinger equation, according to our evolution generated by our Hamiltonian. And we would like to ask questions about the state after the evolution. And of course, we are not interested in the whole many-body wave function because this would require already an exponential number of measurements in our system. Rather, we are interested in some physical properties. So somebody gives us an observable, for example, the magnetization, and the goal is to compute this observable in this evolved state. So make predictions of what will be physical properties of our systems after some time. Actually, that's a problem that was considered many, many years ago by Seth Lloyd, who basically took over Richard Feynman's ideas and he formalized them. And he wrote a quantum algorithm for a quantum computer. And with his quantum algorithm, he realized that the computational time actually scales like with n, the number of qubits that you want to simulate square, and also with the time that you want to simulate square, and with 1 divided by the error that you're allowed. So at the end, you will make some error here when you make that. And so it scales like 1 divided by this error, the computational time. And the idea is very simple. The idea is actually quite obvious. So the idea is that just to start, prepare your quantum computer in the state psi 0, and then tune your Hamiltonian in such a way that it evolves for some time according to that. And at the end, make measurements of this observable in your quantum computer, repeat it many times, and at the end, you will be able to compute this expectation value with an error epsilon. So you have to repeat 1 over epsilon times and so on. And the only technical point is that, so how do you transform the evolution operator into quantum gates? But that's rather trivial. So what you do is that you take your total time and divide it into small steps. This is what is technically called trottarization. And then you notice that if you work for a small time step, this can be translated into some quantum circuit, into some concatenation of logical gates. And this is what leads to this computation. Actually, in the meantime, this quantum algorithm has been improved by a lot. So now the best algorithm takes a time that is linear in the size of the system, is also linear in the time that you want to simulate at the end, and it's case like the logarithm of 1 divided by the error. However, these algorithms are typically not natural for niche devices, and the reason is that in this trotterization, then there is a lot, you have to do a lot of gates. And so typically these niche devices, since they accumulate errors, you cannot do many gates. And that's why it's a challenge now how to implement these algorithms in these devices. For analog quantum simulations, so for analog quantum computers, that's relatively simple. So you don't even need these algorithms, because the only thing that you have to do is just to tune your interactions in your system. So engineer the interactions in your system such that they correspond to the Hamiltonian that you want to simulate. And if you do that, then the only thing that you have to do is to wait for the time that you want to compute and then do the measurements at the end. Actually, there are other problems. Let me go to the second problem. That's the thermal equilibrium. So now again, you're giving a system that you want to study, a many-body system. You translate it, you put it in terms of a lattice, and you are given the Hamiltonian. And then you would like to compute now not the dynamics of the system, but rather the equilibrium properties. So what it means here in this case is that you would like to know properties at 0 temperature, or what is called the ground state energy. So you compute the spectrum of your Hamiltonian, then there would be a low state. This is what is called the ground state. And you would like to compute physical properties of this state. So namely, so you would cool down your system to 0 temperature, what would be the physical properties? And so again, it's the same as before. Somebody gives you some observable and is giving the Hamiltonian and asks you what are the expectation values of your observable in the ground state. This would be the predictions of the physical properties at 0 temperature. And this is very different from what happens with dynamics. So actually, this problem is very difficult. It's in terms of the complexity class is in what is called the QMA class. These are problems that are hard for quantum computers. So that in quantum computer, it typically takes an exponential time. So I don't want to tell you so much because I don't have time about these complexity classes, but this means that this problem here in general, for general Hamiltonians, then would take an exponential time. And so with the size of the system. So of course, you have to compare this with the time that it would take with a classical computer if you have the same resources. So you have a memory still that grows only linearly with the size. And as I told you before, then this is a super exponential. So it's still, even though it takes an exponential time with the size of the system, it's much better than the classical computers, which under the same conditions would take a super exponential time. So there is an advantage, but that's not so clear as the advantage that you have with the dynamics. In fact, another important point is how much is this alpha? You see, if this alpha was 100, then this would be very bad, 2 to the 100 times 10 very bad. However, if this alpha would be 0.00001, and still you would be able to simulate very large systems. And so the best algorithm that exists at the moment, as far as I know, is the one that's in which this scales like 1/2. Okay, so the computational time scales like the logarithm of 1 of the error that you're allowing in the prediction of the expectation value, and scales like 2 to the power n-halves, where again, n is the number of qubits that you have in your system. And I will mention so how this algorithm work. And however, these algorithms that exist, so typically are not applicable neither for niche devices or analog. So these algorithms only work for scalable quantum computers. However, in the last couple of years or a few years, some other algorithms have appeared that solve this problem of ground state properties, 0 temperature properties. There are 2 major algorithms. One of them is based on the adiabatic theorem. It's called adiabatic algorithm. And another one is based on the variational theorem in quantum physics. They're called quantum variational algorithms. So the first one, the goal would be to take the Hamiltonian that you want, for which you want to prepare the ground state and to measure. And instead of preparing and trying to prepare that state directly, you take another Hamiltonian for which you can prepare the ground state very easily. So for example, you take a trivial Hamiltonian in which each of the qubits is just affected by some magnetic field. So these are what we call single qubit Hamiltonians. And for that, it's very easy to prepare the ground state. And now what you do is you change very slowly the Hamiltonian as a function of time and change it up to the Hamiltonian that you want to solve. And if this change is very, very slow, then you will follow the adiabatic theorem, and therefore the ground state will follow adiabatically, and at the end you will have the ground state of the Hamiltonian that you want to find. Unfortunately, for typical problems, one can show that actually this time that it requires for the adiabatic algorithm will be exponential also in the number of qubits. However, it may happen that for some problems this time is not exponential, but is just linear or polynomial or something like that. And then in that case, there will be a huge advantage. The difference between this algorithm and the ones that I mentioned before is that these are heuristics. So here you cannot say beforehand if this will work or will not work. You just have to try. And the same thing happens with variational algorithms. These algorithms, however, are susceptible for being used in NISQ devices and analog quantum computers, and this is why they're very popular nowadays. So people are taking problems, translating them into Hamiltonians, applying these algorithms, and trying to see if they will work with this kind of quantum computers. Okay, let me say something now about finite temperature. So that's very similar, a similar problem that the one that we had before, but now instead of zero temperature, we're interested at the properties at finite temperature. So what it means is that you take the same Hamiltonian as before, the same problem as before, but now what you want to do is not to compute the properties at some particular state. This would be like the ground state if this is the spectrum, but you would like to average with a Boltzmann distribution, and this would be what would describe the thermal properties of your system. And so it turns out that, of course, this problem, since you could consider as a temperature, zero temperature, then it has to be as difficult as the zero temperature case. So it will be exponentially in general. What happens, however, is that if you increase the temperature, there will be a point at which this problem will become easy in a quantum computer. And if you increase the temperature even further, then at some point it will be easy in a classical computer. So for a very, very high temperature, then this problem can be solved classically with series expansions or some other things. But it happens that for earlier temperatures, so even for low temperature, not close to zero, then it turns out that the quantum computer has a window in which it can work and can be efficient. And in fact, so that's something that we have been working on in the last couple of years. And so we have found actually that there is an exponential speed up. So there is a range of energies for which it is possible to answer this question. So what are the physical properties of a state at some finite energy in polynomial time, in a time that only grows like n to some power, not exponential in n. And this algorithm actually is relatively simple, and it's very much related to some notions that we have in optics. Namely, that if you have some spectrum, what you could do if you're interested in some particular energy of the spectrum is just prepare some state that is easy to prepare, that has some mean energy that is around the energy that you want to study. The only problem is that this state will have a lot of variance, okay? So it will not be an eigenstate. And you can do is to use a quantum algorithm to decrease the variance, so to filter in the same way that we filter in optics. And if you do the ideas of optics there, then you can see that there is this exponential speed up for a range of temperatures. And another thing is that this can be used with both analog and NISQ devices, this algorithm. That's, this was for finding the properties of some energy, some particular energy. You can also have another algorithm that we proposed recently that uses similar ideas for finite temperature problems. And in that case, so what happens is that these algorithms gets around what is called the sign problem in quantum Monte Carlo methods. So in quantum Monte Carlo methods, this is a method for classical computers to solve many-body problems, in which what you do is that you sample classical configurations. So you take some classical configurations of your spins or your qubits, then you compute what is the probability of this configuration, and then you change the configuration, compute the other probability, and accept or not, depending on the ratio of these probabilities. And you can do that, and if you can compute these probabilities, then the method converges very well, and then the problem can be relatively easily solved with a classical computer. The problem lies, however, in how do you compute these probabilities that are required for these algorithms. And in some problems, these probabilities can be computed with a classical computer, and in some problems, they cannot be computed with a classical computer. And you say that you have a sign problem in Monte Carlo. And so what the quantum algorithms that we have proposed, what it does is that it computes these probabilities now with a quantum computer. So the idea is that you could now solve problems with a classical computer and use the quantum computer as a subroutine that only computes these probabilities that are required in order to sample classically. And these algorithms that we propose would also work with NIS devices and classical and analog quantum computers. And that's why, I mean, we are collaborating now with several experimentalists and some companies that has these NIS devices in order to implement them for some particular problems. Okay, so now let me just go very briefly about difference between analog and digital quantum computers. So I don't have so much time. So I wanted to mention that there are different possibilities for analog quantum computers based on cold atoms in optical lattices or based on quantum dots in photons, etc., etc. And the advantage of analog of these systems with respect to quantum computers is that they're easy to build. Of course, they have these advantages that they are not universal, there is not error correction. However, I mean, people have, it was mentioned in the previous talk, that, for example, with cold atoms in optical lattices, people have already realized some of these simulations, and they have been able at least to test that this with analog quantum computers, you can answer some physical questions that may be relevant in some other context, like it was mentioned before in the context of Fermi-Hubbard models. Now, in the case of cold atoms in optical lattices, there have been proposals for solving condensed matter physics problems with this system, high energy physics models problems, and also lately quantum chemistry. And so I want to just to finish telling you that about this way of solving quantum chemistry problems with these cold atoms in optical lattices. So it was mentioned before that in atoms in optical lattices, then what you can do is that you can make a lattice in which these atoms are levitated, and now the atoms can hop from one place to another one. And so the idea is that you would like now to simulate with these atoms a quantum chemistry problem. A quantum chemistry problem is where you have a set of electrons that they are interacting with some fixed nuclei in the Born-Oppenheimer approximation, and that the electrons interact with them among themselves. And then you would like to describe either the dynamics or ground states or thermal properties, like I mentioned before. And so the basic idea is to use now fermionic atoms to represent the electrons in such a way that they could move in this lattice from one place to another, and this would represent the motion of the electrons around. So this would correspond to the part of your Hamiltonian that corresponds to the kinetic energy of your electrons. On the other hand, you could have some holographic potentials that such that the electrons, these particles, these fermionic atoms that behave like electrons, are attracted to and are attracted with a potential that can be resembled with these holographic methods, this 1/r Coulomb interaction between the nuclei and the electrons. So this would be an external potential to which these atoms are attracted in the same way that electrons are attracted to nuclei. The difficulty here is how do you describe the the electron-electron interaction? So this would be, how do you make two fermionic atoms in an optical lattice to interact with each other? And this interaction has to be Coulomb interaction. And as it was mentioned in the previous talk, typically, with cold atoms, since they are neutral atoms, they don't interact according to Coulomb interactions, but rather, if you have Rydberg atoms like 1/r³ or 1/r6 potential dependence. And the idea that we had in this paper actually was to copy nature, in the sense that if you consider what is the interaction between electrons, the interaction in quantum electrodynamics is mediated by photons in such a way that one electron emits one photon and it's absorbed by the other electron, and this creates these interactions. So here, what we propose is to use another atomic species that would be a boson, in such a way that this atom interacts with one atom and the other atom and mediates the interaction. And if you do it properly, then you get that the effective interaction is really like a Coulomb interaction. And this is the way that we propose to simulate these small chemistry problems with cold atoms in optical lattices. So with that, I think that my time is up. Just want to finish up just saying that the field of quantum simulation, which is probably one of the most important in the terms in applications for quantum computers, And apart from solving specific problems with this quantum simulation with analog quantum computers or digital quantum computers, I think that this could bring us many other things. It's not only just as a machine that solves problems. So first of all, it can provide us some understanding. So if you have a quantum simulator and then you're solving a problem, then you can also change the parameters in your simulator and look at what is happening in your problem in the same way as you do with an experiment, that you can learn about the physics of some system with your experiment. So the quantum simulator in that case would be like an experiment that is describing or investigating the physics of the system that you want to do. And apart from that, I think that they will be very important for benchmarking theory. So there are many theories now, in particular tensor networks, machine learning-based theory to describe many-body systems. And some of these problems cannot be benchmarked because there is no way of checking if the solution is giving exactly the correct result. If we had one quantum simulator, then we could benchmark theory and therefore develop better theoretical methods. Somehow the challenges, apart from experimental and technological, so at the moment there exist these devices with analog quantum simulators. However, one have to scale them a little bit more and to make them a little bit less noisy in order to have cleaner results. And also another very important aspect is how to connect these quantum simulators, some industrial interests. So there are chemistry companies and some other companies that are interested in solving some of these problems. But indeed, can we make some impact with these analog and NIS devices already now in the industry? And with that, I would like to finish with a picture of my department and the people who have been involved in these things that I have mentioned, and especially my Carmen Bañuls is here, and Sirui Lu, who is here, who were related to these algorithms that I presented here. So thank you for your attention.
Thank you very much, Ignacio. If I can call you by your first name. Do I pronounce it correctly?
Perfect. Thank you.
Thank you. It is so challenging that it's hard to know where to begin. Of course, for people like me, the idea of using the quantum simulator to generate probabilities is, of course, very close to what we would like to do. But first, I should also let other people ask. I'm sorry, Letitia, I don't see questions in the chat. Okay, if then the idea that I think also the next speaker, so our speakers today are connected in many challenging ways, is how to solve. I mean, solving many body problems is important and potentially essential if we want to design drugs, because the drug industry is a very major consuming of computing power. And but I want new physics to. I don't so much want to solve many body problems, because in the end you have to design drugs in the laboratory. But the possibility of mimicking physics that we don't have, that's what I would regard as such as machine learning, that would be discussed by the next speaker. The interface between information theory and quantum computing is what I'm really looking for. But I see we have a question that thanks you, of course, for your nice presentation, but okay. Do you think that the very recent noise limitation results of Stick-Franca and Garcia pattern of classical simulability on noisy quantum devices applies for heuristic methods for VNIST.
I agree with you, Rafi, that it's very important to use these devices to discover new physics. And in fact, that's something that is already happening, in particular for exotic matters, exotic phases of matter. So people are now investigating topological phases of matter and many other. And then I think that it's very important that these things also happen with these quantum simulators that are able to go beyond what we can do, let's say, with analytical or numerical tools. And this is happening at the moment. So I'm very happy that in particular in our institute, people like Immanuel Bloch are doing some this kind of experiments. Now, related to this question, so I don't think that these limitations apply from this paper that was mentioned. I mean, that these are formal results that are important, but not applicable to the problems. I can give you I can give you just one example. So imagine that you have a Hubbard model, and like the one that was mentioned in the previous talk, and imagine that your system is noisy. And so there are some errors. Your Hamiltonian has errors that are extensive. And at the end, you're cooling your system, and you can cool it. And then you would like to know whether the phase is superconducting or not. You want to know you have D-wave superconductivity for some particular parameters, because that's one of the questions for the Hubbard model. And what you could do is to measure simply. And even if your errors if your simulator has errors, since this phase is robust, then you will see superconductivity. Maybe you will not get 10 digits of what is the resistance there, but you will be able to see that there is superconductivity, D-wave. And actually, that's something, this question is we cannot answer with classical computers. So you see that already at that very simple level, there are advantages.
Thank you. I have a notice from our technical people that I have to thank Professor Sirac and close this room. So we thank you very much. If possible, please stay for our round table, and I am closing and inviting you all to the next room. Thank you.